kind of topology. So exercise 2, you can do it with paper and scissors. So you take a Möbius band. So you take a Möbius band. This is cylinder, so this is not Möbius band. So I want Möbius band, so I twist this. This is Möbius band. So you know that maybe you have seen that if you cut the Möbius band in the middle, what happens?
In the middle?
So two Möbius bands,
Yes.
and they become linked together. But what happens if we cut like in one, not in the middle, but in one, for example, of 1/3 distance? So the behavior change. So you can see what happens. In the middle, what happens?
Different parts.
So there is one case where it becomes bigger Möbius band, and one case where they become two Möbius band. So you can do that exercise, but the exercise I want you make is that so the same. We take Möbius band. Now we glue here. So this is like a cylinder, but we also make Möbius band. We glue two Möbius bands. Then you cut in the middle and see what happens. It will happen something very curious in this example. So you cut with scissors along the middle and see what happens. Any question or comment? So that is like introduction to the course. So now what we study is nodes, only nodes for several times. But I wanted to say this so that you become familiar with this kind of topology, how we think in topology, that we never think in that final intersection of open sets is open, never appears. Question or comments? Okay, so let's start. The knot theory is also very old, so Gauss, he was thinking in knots mathematically. His student, but for them was very curious subject. They don't have idea why it was interesting. So some people became interested in this because this person, some physician, he was thinking the model for the universe, for the what is the name of this? La materia. ¿Cómo se dice materia?
Material. Matter.
So he was thinking model for matter. So now we have the atomic model. But before, so they didn't have. So he was thinking that the matter are some kind of nodes of ether. this magic material that we know that does not exist. But in the past, they think this material exists, and they think that this material becomes noted. And the different materials is different nodes. So they start to make tables of nodes. So this will be like some oxygen or something, and this should be a different material. And they start to make tables of nodes. But of course, this theory is not true. So the atomic model is much better in reality than this. This was just some trial. But then mathematicians become interested in this because it's a very interesting problem. How many nodes do we have? How to know if they are different or not? And at that time, so they were able to make tables until 11 crossings. So we call this the crossings. So this is 1, 2, 3 crossings. This is 1, 2, 3, 4 crossings. And they make very big tables. But they didn't know how to study until algebraic topology appears. So algebraic topology is the subject that allows us to answer, for instance, that these two nodes are different. It's a difficult question. How to know if, so this maybe, nice. So we take some piece of strand and we make some node. So we have some node. How to know if this is trivial or not? Or other person make other node. How to know if they are the same or not? And the idea of being the same is that I can deform. So they are isotopy. So this is difficult task in general because we can try to deform one into another, but we don't arrive to do it. So, but this does not mean that there is not some magical way to do it. So this implies the development of many mathematics. And it has connection with many subjects. Our definition of knot. So we have S1, a knot with us. It's a good map. From S1 to R2. So what is the meaning of good here? So it depends on your interests. So if you like differential geometry, so we want a smooth map. But if you don't like differential geometry, we don't need that condition. We just need that, like here is one. So this is like a smooth map. But if you don't like differential geometry, it's enough to say that the image of this map we can draw with polygons, a finite number of polygonal lines. the same theory, so we can work with any of them. Of course, we made the drawings like this always, but we can make like this. What we want to avoid is that, so what we want to avoid with this definition here of good is that we don't want that something like this happen. We have good knot, but then here the knot repeats itself smaller, and here repeats again smaller, and here repeats again small. We want to avoid this kind of thing. This is still like continuous map, but it's not smooth because there is some accumulation point. So we want to avoid this. Because the theory behaves very different. Here and here is very different. So this is very complicated project. Because every time we take a neighborhood, local neighborhood, here we will see something notable. But here, when we take local neighborhoods, we see images. So the theory here is totally different. In Mexico, some people study. These are called wild nodes.
Wild nodes.
Can you say fractals are also defined by?
Yeah, this is like fractal behavior. Similar. So it's very difficult to study. Some people study this, but this is very known in general. So we avoid that. We will give examples.
Professor,
Yes.
for nodes can we use two strings or always there will be one string?
Here we have only one, but we will allow several.
Okay.
Say several again. Link.
Link.
The link we have several copies of S1.
Okay.
2, 3, 4. Instance. So node is only one component and link to several components. Let's see examples. Or trivial embedding and node. This one that I control several times. Here for example. This is called video elements. Do some links. Trivial link of two components, use two circuits. Two links, two circles linked in this way. Called home link. This one was interesting. It's called white hat link. several examples. These have names, so they have very important properties in general. So they are very important in several branches of mathematics. So what we want to study is how to know if they are different or not. For instance, how to know that these two are different, or are they the same? How to know if they are different or the same? For instance, what can we answer here? This one and this one. Are they different or not?
It is by two strings, it is by one string.
So what is, so this has one component, this two
Has two
components.
Yes.
So we are using some kind of invariant, a number. So the number here is 2, the number here is 1,
Yes.
so they cannot be the same.
Okay.
But what about these two? This has two components, two components. How to know if they are different or not? Or these two. So that is what we are going to study. So tomorrow we continue with this, and where is the paper with the images? So I will create some Google Classroom page, and I will update some books, like reference books and some exercise. And on Wednesday, we will make only exercise. You will make exercise. Any question you have, you can write me or ask me. Thank you for coming.
Maybe we can-